Hello, everybody. Welcome to Unit 0, Section 2, where I'm going to be walking through some other concepts of general chemistry. The big concept in chemistry, of course, is going to be the mole, and I'm going to walk you through some basic conversions that we see along the way with that. This is a graphic that I use in general chemistry all the time about how to use Mole Island as our friend in terms of mole conversions. You'll see right here in the middle, there's a lot to process with all of this, but right in the middle of all of this is our core of the mole. The mole is defined as an amount of a substance, and we can actually in chemistry refer to that in three different ways. We can refer to amount of a substance in terms of mass, we can refer to it in terms of particles, and we can refer to it in certain conditions called STP, standard temperature and pressure, a volume of a gas, we can find in terms of liters. And so there's different ways we can apply this, but the concept is 1 mole of a substance is going to be what we call Avogadro's number. I'll revisit this in a second, of number of particles in there. And so we have this is kind of a tricky little area in there when we talk about number of particles, because in chemistry we can't see atoms, we can't even really see whole molecules with it unless we're using special equipment along the way, but we can actually quantify how many particles are found inside. So we have some questions to be answered with those, and I'll show you with examples. We can also take a look if I have a certain amount, what's the mass of that thing going to be? Or, and the biggest extension is, if I'm given a certain mass of something that I measure in lab, how many particles would be found inside? You can see that we're going from the mass to the mole and then down to particles. And then in Gen Chem, we're not going to do this quite so much in AP chemistry, but in Gen Chem, we can also take a look at the volume of a gas under certain conditions. And that number is going to be a 22.4. The reason we don't use that as much in regular AP chemistry is because really the reality is we're not going to be under those conditions very often. And so it's just the concept of using 22.4, and we're going to do other things with gas laws. And you can see how this all fits in. Okay, I'm going to focus on the bottom two legs of this, and so I'm going to be showing you how to do different mole conversions to get you an idea of how the factor label works and everything else. In dimensional analysis, it's just how the process of showing your work. Remember, AP College Board does require you show all your work. Even if you have the correct answer and no work shown, you don't get any credit. So you better get used to showing and documenting those steps. And the best reason I can give for that is because if you are off in a little bit, this system shows a very easy way of tracking the steps. And so you can find and isolate your mistakes very easily. So if we're going to be focusing on the first of the legs in terms of particles and mole conversions, we've got to get under our mind and under our belts the concept of Avogadro's number. 1 mole of anything has 6.02 times 10 to the 23rd representative particles. That is a number you need to memorize. And so this is the question of how do we actually use it and implement it. Now, what we mean by particles, if it's a single element, we're talking about number of atoms. Okay, so if I have a mole of, say, carbon, there's 6.02 times 10 to the 23rd atoms of carbon in there. Now, if it's a compound, that gets a little bit trickier. We refer to the compound then in different ways. And we're all used to more of a molecular compound, but there's also an ionic compound like sodium chloride. We refer to the sodium chloride compound in terms of particles as formula units or F units. Okay, so that when you hear that or see that phrase, it's just talking about an ionic compound in there versus what we're all used to seeing more commonly just out in general public is the concept of molecules. And we abbreviate that MOLEC. If you say MOL, that's moles, or MOLE, or if you just do M, that could be molarity, or all these different things. It's just how we abbreviate them. So 1 mole is 6.02 times 10 to the 23rd formula units of chalk, or 6.02 times 10 to the 23rd molecules of water. Okay, so here's how we do this math. Okay, the concept, I'm going to walk you through the steps of this, go kind of fast with it, just to brush off some of those skills of conversions along the way as well. I want to know how many moles of magnesium is in 1.25 times 10 to the 23rd atoms of magnesium. So notice I have an element in here, and so we can go directly from atoms into the mole because it's a single element. So I start with the number that's being provided. Now remember from the first video, this number is actually a measured number. Sorry, this is the measured number and this is my estimated number. And so times 10 to the 23rd atoms. And so I'm going to get rid of that label of atoms and go directly to the mole. I can do this in one step because it's a single element. 1 mole is 6.02 times 10 to the 23rd atoms. And so I end up with an answer of 0.2076 if you just apply the math in your calculator. Now, I'm not done. Remember, in chemistry, we always have to round according to significant figures. And so here I have 1, 2, 3 values that were measured. That last one was estimated, so he counts. 1, 2, 3. The next number is greater than 5. So my actual final recorded answer is 0.208 moles. And don't forget to label everything along the way. And technically, I should have moles of magnesium. Okay, so that's the concept with that particular set of conversions. I can go atoms directly to the mole because it's an element. Okay, now the next one is going to be doing something a little bit different. Okay, a variation of this. And I'm going to get better along the way. Don't worry, I'm going to get better with how to erase and be more efficient with it. This is just kind of introductory, getting used to it. Okay, atoms in moles, and so we're going to be going the other direction with it, aren't we? We're going to be asking how many atoms are there. So I can take my mole of zinc, and it is an element, so I can go straight to atoms. Okay, we always have to pause there and verify that. So 1 mole of anything is 6.02 times 10 to the 23rd. And so I just apply the math with that one. I end up with an answer of 9.03 times 10 to the 23rd. And then I look, I've got 2 significant figures, 1, 2. Next number is less than 5. And so that becomes 9.0 times 10 to the 23rd atoms of zinc. Okay, and to help out the reader, you always put a box at the end. Okay, always help your reader see where you're at. Otherwise, they look to the very last thing recorded, and it can be a little confusing for them along the way. Now, notice that I've been emphasizing this question about the atoms along the way, and this time I have a compound. Okay, I have 2.12 moles of propane. Well, I can't go directly to the atom because I have a compound. In fact, it's a molecular compound. Instead, because it's a molecular compound, I have to go from moles to molecules first. And then I ask the question, how many atoms are in that molecule? Okay, so it's a 2-step problem along the way. 1 mole of anything is that many particles. But since it's a compound, those particles are called molecules. And then I ask the question, in 1 molecule of C3H8, how many atoms are there? Now, I said atoms in general. I didn't say how many carbon atoms or hydrogen atoms. That question sometimes comes up too. We'll practice that along the way. Here, I'm just saying overall, we'll have 3 carbon atoms. I have 8 hydrogen atoms. So that's a total of 11 atoms total. And so I end up with 1.404 times 10 to the 25th atoms. Now, I'm not done. I have 3 significant figures here, 1, 2, 3. Next number is less than 5, so I have 1.40 times 10 to the 25th atoms within C3H8. Now, the question is this 0 significant? It's a trailer 0, so he counts. Okay, that goes back to significant figures and all those other things. Now, when we get over to the other leg of molar conversions, we're getting into masses. And so you're going to see this concept of masses, and we look to the periodic table for all of that to figure out our gram atomic mass. Okay, now this is just saying what's the mass of something. Technically on the periodic table, those are not grams. They are grams if you have a mole of that substance, but on the periodic table, when you see those values for atomic masses, those are average atomic masses, and those are what we refer to as atomic mass units, or AMUs, okay? So we could ask the question, first of all, if I had a mole's worth, what's the formula mass of sulfur trioxide? Okay, this isn't sulfite, because there's no charge on there, it's sulfur trioxide. So make a record, first of all, of how many of each element you see. I see 1 sulfur, and so that's going to be 32. And I see 3 oxygens, and that's going to be 16 each. Okay, so 32 and that's going to be 48. And so the mass of the gram atomic mass of sulfur trioxide, or if I had a mole's worth, that would be 80 grams. Okay, so that's the concept there, getting into the formula masses. Now, we'll certainly get more complex with this, and the next level would be then distributing. When we see something like ammonium carbonate, this gets a little bit tricky. I see a parentheses here, which means mathematically I'm going to distribute that 2 to the nitrogen as well as the hydrogen. And so I have 2 nitrogens, I have 8 hydrogens, I have 1 carbon, and I have 3 oxygens. Nitrogen has a mass of 14. This is 1. This is 12. And I know it's 12.011, but that's fine. And this is going to be 16. So this is 48. This is going to be 12. This is 8. And I see 28. So you see the pattern when we figure out formula masses along the way. The formula mass of, or the gram atomic mass of ammonium carbonate is going to be 96. And it's just some basic math of distributing along the way, using our periodic table for it. The mole conversion is to find formula mass. Now, we use that concept to figure out how many grams there are if I'm given a set amount of this. So this is something that we'd be measuring in lab. We have 9.45 moles of my dinitrogen trioxide. It could have been something ionic, but this happens to be molecular. Well, I see I have 9.45 moles of dinitrogen trioxide. 1 mole of dinitrogen trioxide. The question is, how many grams would 1 mole constitute? Just 1 mole. So I see, okay, we have 2 nitrogens, I have 3 oxygens, and again, just going really quickly through this, that's going to be a 28, and that's going to be a 48, and so that's going to be, what, 76 grams. 1 mole's worth is 76 grams. I don't have 1 mole's worth. I have 9.45 moles worth. Okay, so I just kind of do that quick, simple math along the way and round accordingly. Okay, now let's take a look at another example, and we're going the other direction with it. Now remember, I've thrown in an example of a Roman numeral. That Roman numeral tells me the charge of the iron. So the Roman numeral 3 means that I have a charge of a +3 and oxygen's a -2. So I'm going to convert the other way and go grams of iron 3 oxide. Remember, swap, drop, reduce. And I want to know how many moles. So notice that the grams are going to cancel out. And so the question is, 1 mole is going to be equivalent to what's the formula mass? So 2 irons, and I have 3 oxygens, and we've already said this is 16, so that's 48. The mass of each individual iron is going to be a 55.85. And now here we're going to have to slow down a little bit to make sure we're getting all of our values in there. 111.17 plus 48. That gives me a formula mass of 159.7. 1 mole is 159.7 grams. Okay, so if I multiply this one out, I end up with a 0.5773, but we have 3 significant figures, 1, 2, 3. So that's going to give me a value of 0.577 moles of iron 3 oxide. Okay, so that's how we delineate all that and do a conversion using a dimensional analysis technique. Okay, now we can apply the same thing. This is actually what we're building up to in saying how many particles are totally in there. We can account for everything, and this is as complex as it gets. I'm given grams of a compound, and I can go from grams to moles. But then when I go to moles, if you remember, this is of a compound. I can't go right to atoms, even though that's ultimately what I need to do. I have to stop and go to molecules first, because it's a compound, and then I can ask the question, how many atoms are in that molecule? And so 1 mole, I have to figure out, okay, so 3 carbons, 8 hydrogens, this is 12, this is 1, so that's going to be 36, and 8, that's 44 grams. Okay, 1 mole is Avogadro's number. And then I say, okay, within the C3H8, 1 mole has 11 total atoms. And so I end up with an answer here of 3.1906 times 10 to the 23rd, and there's 3 significant figures, 1, 2, 3. The next number is less than, so that's a 3.19 times 10 to the 23rd atoms. Okay, so that's how we show all of our work in doing a dimensional analysis. Notice that it's one fluid conversion. We don't stop and pick up our calculator at different times and so on. I'm doing this in real time so you see the thought process behind it. Now, another concept with this, and this is going to be one of our first labs, is finding the percent composition of something. Okay, if I'm given a compound in there, I want to know what percent of that compound is maybe carbon. If you look at fertilizers and all that, at different times of the year, you put different fertilizer on your lawn because you at one time of the year might need more nitrogen. Another time of the year, you need more phosphorus and so on. So we can actually figure this out by mass. Okay, there's a couple of different variations of what this problem might look like. And so we can take a look at an example where we see a certain amount of each element, and we want to know what the percent composition is of that element. If the compound has this much magnesium in it and this much oxygen, I can actually figure out the percent of magnesium in that particular compound. Okay, so I would simply have to ask, when we see percent compositions, like percent of anything, it's the part divided by the whole. How much is in there versus the entire collective sample? And so we would have to add up what the mass of the sample would be first. I have 13.6 grams of the compound, and 8.20 grams of that is considered to be magnesium. And so I would simply take that and multiply, because it's a percent, multiply by 100%, and I see that I get 60.29% magnesium. Okay, the remainder would be oxygen in there. But I'm not done here, because I have 3 values. This is a tool that measured down to the tenths, and so I estimated the hundredths, or it was estimated for me. So I see 1, 2, 3 significant figures, and so I would round that answer to 60.3% magnesium. Now, from there, you can see the rest is going to be oxygen. It's just kind of assumed in general chem, or in AP Chem with that. If you have to figure out the different amounts from there, you could just subtract from 100, or you could just take your 5.4 divided by your 13.6, and you get the same thing. Okay, so that's the concept behind percent compositions, and you should have enough to be successful in lab. And again, just a general review of how do we do conversions within AP Chemistry when we're dealing with the mole. Okay, good luck to you, and we'll check in with you in a future video.